Sathyabama Institute of Science and Technology.
Hello, good morning everyone. I am Dr. Rajalakshmi, Associate Professor, Department of Computer Science and Engineering from Sathyabama Institute of Science and Technology. Today I am going to talk about explore AI with model-based design. So here we are going to see how the model-based design occurs in artificial intelligence. So here we are going to concentrate on virtual sensor modeling, system identification and ROM, and then reinforcement learning. So here virtual sensor modeling, so how it is participating along with the AI. So here we are concentrating on voltage, current and temperature. So these all deals with the AI along with SOC. Next, we are going to see how the virtual sensor modeling involves the software algorithms to make the measurements of physical sensors. So, in this approach, we are going to calculate through the mathematical models, and we are going to get the historical data, and the techniques which are computed here gives the approximations of the sensor data accurately in real time scenario. So, virtual sensors are particularly, it is useful in the real-time scenarios where physical sensors or which are too much expensive, and data augmentation is also needed for that. So here we are using different types of models. The first one is mathematical models, which uses the principles governing the system. For example, if you are using a thermal system or heat transfer equations, they can be used in this mathematical models for calculating the accurate data. Next, we can use the data-driven models. So this second one, data-driven models mainly concentrates on historical data, where machine learning techniques are used for predicting the sensor outputs. So here in this data-driven model, we are using regression, neural networks and machine learning algorithms, which are mainly commonly used. The next third one is hybrid models. Here the hybrid models which is a combination of physical as well as the data driven models, and it enhances accuracy and robustness. Next, we are going to see the applications of a virtual sensor modeling. So here the virtual sensors, these are mainly used in the various industries like automotive, where we are going to estimate the tire pressure, or in aerospace department we are using for monitoring aircraft components, or in manufacturing companies how the process control is being carried out, and it is also used in environmental monitoring. The basic advantage of using this virtual sensor modeling is we can reduce the cost as well as we can improve the system reliability, and here physical sensors cannot be deployed that much easily, and we can enhance the predictive maintenance capabilities. So the major challenges what we are facing in this virtual sensor modeling is noise. So where there is a incomplete data and we have to validate the virtual sensor outputs against real world measurements, these challenges should be faced in the virtual sensor modeling. These are the virtual sensor modeling diagram, where how it is generated, how it is model selected, how the parameters is been tuned, and how the validation and testing has been done. So here the virtual sensor machine learning model, which uses how it is using the measuring the historical data. So these things are given here, and the workflow of the data preparation in AI modeling, and how the system uses a simulation for the deployment of this virtual sensors using AI. So here these are all the applications where it is popularly used in industries, that is automotive industries, medical devices and aerospace, and industrial automation and machinery, energy production, and the applications where we are using the control systems, electrification and predictive maintenance. Next, we are going to concentrate on system identification and ROM. Here, system identification, which uses the mathematical models of dynamic systems of measured data. So, how it is involving the data collection and the model structure selection and the parameter estimation has been gathered in the system identification. So, here the input and output data, whatever we are collecting, that is used in the system under various operating conditions. The next thing we are going to see is the mathematical structure for the model, which uses linear, non-linear state space transfer function. And the third one is a parameter estimation. We are going to determine the values of the model parameters, and the collected data should be having the best fit. So, the next thing, the techniques whatever we are using in system identification is method of least squares and maximum likelihood and other optimization algorithms. Next, we are going to see the model validation. So, here the model's accuracy and using validation data sets, we are going to determine the system identification. Applications of using this system identification is control system design, and we are going to detect the faults and we are going to diagnose the faults, and we are going to predict and forecast. So, these are all the applications used. Next, we are going to see about the ROM. The main thing about ROM is reduced order modeling. So, here reduced order modeling, this is a process of simplifying a high fidelity model while preserving essential features and dynamics. So, ROM, it is used to reduce the complexity, computational complexity, and make simulations more tractable. So, the next thing we are going to see how the model reduction techniques are used. So, here the first one is we are using is a proper orthogonal decomposition. So, POD is used to identify the dominant nodes in the system and the original model where it is having low dimensional subspace. Next, we are going to see the balanced truncation and moment matching Krylov subspace methods. So, these are all the state space model and the reduced model which are used in the reduced order modeling. So, the main applications used in the reduced order modeling is it is used in the real-time control and optimization, multi-scale modeling in fluid dynamics and structural analysis, and parameter studies and design optimization is done. The major challenges faced by the ROM is ensuring accuracy and stability of the reduced model. So, here we are going to capture the non-linear dynamics and complex interactions. Next thing, the integrating reduced models for larger simulation frameworks. The basic thing we are doing in the virtual sensor modeling by combining with the AI, where we are particularly using the combination of system identification and ROM. So, here how we are combining the system identification and ROM. So, the ROM techniques which are more efficient and they are used in real-time applications and large simulations. So, how the workflow is going to be done in the combining the system identification and ROM. So, here first we are going to collect the data and we are going to identify the system, and then we are going to reduce the model and do the validation and implementation is done. So, this is the basic diagram for reduced order modeling where it is using high fidelity model. Now, this is a reduced order modeling the basic architecture diagram where it describes about the basic how the model is using the high fidelity. And next we are going to see the reinforcement learning. Reinforcement learning, basically it comes under the machine learning technology where there are three things: supervised learning, unsupervised learning, and then reinforcement learning. So, reinforcement learning mainly deals with the agent and the environment. So, here we are going to get the actions. So, according to the actions, the rewards or punishments will be given by using the reinforcement learning. So, here this is the architecture diagram for this, and the next thing we are going to concentrate on training humanoid walker. So here training a humanoid worker is a tedious process where we are going to develop a control system which uses a bipedal robot to walk, balance and navigate its environment. So this is a complex task of modeling. It is combining the modeling, simulation, machine learning and robotics. So the basic key steps used for humanoid worker is how to model the humanoid worker. So here first we have to create the simulation environment where control strategies and reinforcement learning transferred to real hardware has been used here. So first we are going to concentrate how the modeling occurs. So kinematics and dynamics modeling, it has 3 steps. So forward kinematics, inverse kinematics and then a dynamic model. These are the things which are used to control the robotic actions. And then we are going to see the physical parameters, how we are considering about the humanoid worker. So here we are concentrating on mass, center of mass, inertia of each link, joint limits and ranges of motion actuator characteristics. So where the speed and torque limits has been calculated here. The simulation environment, for this we are using the simulation techniques like software tools like Gazebo, Mujako or PyBullet. These are the simulation tools which are used in humanoid worker in a virtual environment. Next, we are going to incorporate sensor models, IMUs, force sensors to mimic real world sensing. So these are all the things comes under the simulation environment. Next we are going to define the task. So how to walk or how to walk on the flat ground or navigating uneven terrain or terrain or climbing stairs. So by using that, whatever task has been performed, the rewards has been given to minimize the energy consumption and maximize stability. So the basic control strategies which are used are classical control. This deals with the PID control. So this is proportional integral derivative control. And then model predictive control, MPC. The advanced control which is using zero moment point and whole body control. The basic things we have seen in the reinforcement learning and how we are going to formulate the problem. So here we are going to define the state space and we are going to define the action space and we are going to reward function. So these are the things we are doing. How the training algorithms are used for making the humanoid worker. So here deep Q learning which is used in the neural network to approximate Q values for different state action pairs. Next we are using proximal policy optimization and soft Actor-critic. This is used in reinforcement algorithm to optimize a trade-off between exploration and exploitation. Next we are going to see the training process, how we are processing the training by simulating the episodes of working and collecting data on states, actions and rewards. Next we are going to see the data, how to update the control policy and how to iterate the process to improve the policy over time. Here we are using the transfer to real hardware. This is sim to real transfer where we are going to fill up the reality gap by ensuring the simulation accurately how it is used in the real world physics, and we are using the domain randomization and we are going to implement the learned policy of the physical robot and fine tune as necessary. The basic safety consideration what we are going to do in the humanoid walker is we are going to implement fail safes to prevent falls or damages of the robot. We are using external support during this initial testing phases. In this frameworks and tools, we are using robotics operating system and OpenAI GM and TensorFlow PyTorch. So these are all the things which are using in the while training the humanoid worker. And the practical considerations, these are the challenges we are going to see for making the humanoid, training the humanoid worker. So sensor calibration and noise handling, real-time processing requirements and robustness to external disturbances, energy efficient and battery management. So the main thing is we are going to train the humanoid worker. So various challenges has been faced by using the neural network techniques and deep learning techniques, we can control the robots, humanoid worker easily. Thank you.